polynomials is recognizing that the x and the x squared, the x cubed are place values. So let's look at the next visual, and it has two numbers. I call the first number 300 negative 27. And I ask my students, what is 300 negative 27 equal? And they have no idea. Well, again, place value. The 3 is in the hundreds place, the negative 2 is in the tens place, and the 7 is in the ones place. That is 300 minus 20 plus 7, which I believe is 287. The reason I bring this up is because with polynomials, since the place value is given, we can have negative numbers as well as positive numbers as the coefficients, that is, the numbers in front of the x or x squared, which are equivalent to the digits in our place values in our whole numbers. The second number on your screen, 357. You may giggle a little bit. Hefty, what does that mean? Well, if something is in a tens place, we put a ty next to it, right? 50, 60, 70. This is hefty. What's that equal to? 300s. Half a 10 is 5. 7 ones makes 312. Again, with polynomials, we could use fractions as our coefficients. You could have a half x or a half x squared or 2/3 x to the third, etc. Let's take a look at the next visual. This is some other examples of things that you can do with a polynomial because the place values, the powers of x, are shown. The first one has 3x squared minus 4x plus 2/3. Again, we have a negative number in there and a fractional number. You couldn't do that with whole numbers. The second one, 5x cubed plus the square root of 7x, has an irrational, a square root number, in one of the place values in front of the x. Also notice in the second polynomial, there's no square term and there's no whole number or constant term. That is, if this, for example, if we had a number like 5,070, we'd have a 0 in the hundreds place and a 0 in the ones place. We don't need those zeros in polynomials because the place value is shown. So we just put a 5 in front of the x cubed and a plus square root of 7 in front of the x. Now, what we're going to do in the rest of this lesson is add, subtract, and multiply polynomials. And the thing I want to impress upon you is that assuming you can add, subtract, and multiply whole numbers, then polynomials are no different. But we're going to go ahead and restate the rules. For example, in adding whole numbers, the key is lining up the place values, adding all the numbers in the ones place together, the numbers in the tens place together, the numbers in the hundreds place together. You can't add a number in the tens place to a number in the hundreds place. You just can't do that. It's against the law. It's against the law because adding is really a form of counting, and you can only count or add things that are alike. Now, the nice thing about polynomials is there's no carrying. Some of you may think back to first or second or third grade, and you struggled with learning how to add when you had to come down a column and then carry something over to the tens place, add down the tens place, and carry something over to the hundreds place. We don't worry about that because you can have a number as a coefficient in front of the x or x squared that's bigger than 9 because there's no limit, there's no place as such. So let's take a look at the first addition problem, which is 2x cubed plus 3x squared plus 7x minus 4 plus 5x squared minus 9x minus 2. Now, the first step we said is to line up the place values. And notice beneath the original problem is the problem rewritten with the squareds and the x and the numbers all lined up. All we have to do now is simply add. Since there's no x cubed number in the bottom polynomial, we just bring down the 2x cubed. Just as if there was a 2,000 in our top number and no digit in the thousands place if we were adding two whole numbers. 3 plus 5 is 8, so we have plus 8x squared. A positive 7 and negative 9 is negative 2, so we have negative 2x. And a negative 4 and a negative 2 is negative 6. Thus, our answer. Now, let's take a look at the next visual because it looks the same problem. It is the same problem. It shows the original problem and the answer. But also what we're going to do, and this is a very good way to check polynomial arithmetic problems, is plug in, that is substitute, x equals 10. So if we do that, the 2x cubed plus 3x squared plus 7x minus 4 becomes 2,000 plus 300 plus 70, 7 tens, minus 4, or 2,366. And the 5x squared becomes 500 minus 90 minus 2, which is 408. When you add those two numbers up, you get 2,774. If we plug x equals 10 into the answer, the 2x cubed is 2,000, plus 8x squared plus 800, minus 2x minus 20 minus 6. 2,000 plus 800 minus 20 minus 6 is 2,774. Our answer checks. If it checks for 10, you know you are right. And it's very, very important in any work you do in algebra, wherever possible, to check your work. Okay. Now, that takes care of adding. How about multiplying? I always like to ask people, first of all, what multiplying is. And you should remember back from 3rd grade that multiplying is repeated addition. So when we multiply, we're actually learning a way to add quickly. So 3 times 8 means 8 plus 8 plus 8. Now, some people learn to multiply and just do it by rote, having no understanding of what they're doing. So what I'd like you to do is take a look at this next visual, a multiplication problem right out of your 4th or 5th grade arithmetic book. 427 times 381. Notice there's an arrow from the 3 to the 2, or between the 3 and the 2. 3 times 2 is 6. My question to you is, where does the 6 go? Now, most people I ask this of, they want to start multiplying with 1 times 7 and then 1 times 2 and then put it, no. 3 times 2 is 6. Where does the 6 go? The 6 goes in the thousands place. And the reason it does is because the 3 is in the hundreds place and the 2 is in the tens place. And when we multiply digit times digit, 3 times 2, and place value times place value. In this case, hundreds times tens. So the 6,000 is the answer, and therefore the 6 goes in the thousands place. If you can understand this, and again, multiplication is digit times digit and place value times place value, then multiplying polynomials is a breeze. And the reason is very simple. Each polynomial is made up of these terms called monomials, mono being one nomial. So for example, if I was to multiply 2x squared by a negative 3x, that's a monomial, 2x squared, by another monomial, negative 3x. How would I do that? Well, the coefficients, the number, the constant in front of the variable, the x or the x squared, is just like a digit. And we said multiplication is digit times digit. So I would multiply 2 times negative 3. And since we multiply place value times place value, I'd multiply the x squared times the x. So as you can see in the next visual, 2x squared multiplied by negative 3x equals negative 6x cubed, since x squared times x is x cubed. Notice also each of the monomials are in parentheses, and there's no symbol between the parentheses. You may recall from your previous experience in algebra that if you have 2 letters or a number in a letter without any symbol in between, that means multiplication. We don't want to use an x to show multiplication because then we get that confused with the x for the variable x. And therefore we use parentheses to separate the terms and to show that it's multiplication. If those parentheses weren't there, you might think it was 2x squared minus 3x, a subtraction problem. Okay. Now, let's take a look at a multiplication problem in polynomials that's not very different from a multiplication problem you might have done in, let's say, 4th grade. The next visual shows you 3x minus 5 times 3x squared minus 4x plus 3. To me, this is no different than multiplying a 2-digit number by a 3-digit number. We do it exactly the same as we did it in 4th or 5th grade, and I'm sure as we still would do it today if you didn't have a calculator handy. The only difference is that we multiply x times x, it's x squared, rather than 10 times 10 goes in hundreds place. So the first thing we do, we start with the bottom number, the rightmost column or place value, the negative 5, And the next visual shows us that we multiply the negative 5 first by positive 3, then by negative 4x, and then by 3x squared. And we get negative 15x squared plus 20x minus 15. Simply multiplying each of those terms by negative 5. Okay? The next visual takes us to the second line, because now we're multiplying by the 3x term. And obviously when I multiply 3x times positive 3, I get 9x. And notice the 9x is lined up with the 20x, because we're eventually going to add, just like we did with whole numbers, and we only can add things that are the same. We add x's and x's, x squareds and x squareds. Continuing on, multiplying by 3x, we get negative 12x squared, and we get 9x cubed. Now, just as you did in 4,